Okay, our second speaker of this afternoon session is Yakov Veryovkin from High School of Economics. He's going to speak about the real algebra associated with the lower central series of right-angled Coxeter groups. Please.
Thank you. I'd like thanks to organizers for inviting me here. It's great pleasure to talk in Toronto and Fields Institute. My talk is the Lie algebra associated with the lower central series of a right-angled Coxeter group. Let K is a simplicial complex on the set M, where set M is numbers from 1 to M. Also empty set in K, and the elements of simplicial complex is a simplex. Let XA, bold XA, a sequence of pairs of spaces where AI is subset of XI. Given subset of M, I subset M, V has XA power I, like this, product of gamma I, where gamma I equals XI if I in big I, and AI if I not big I. Okay. The K polyhedral product of bold XA, X like this, is union by all simplexes from simplicial complex K, where this union is taken inside product XI. We have notation. XAK is bold XAK when all XI is X, all AI is A. And we have else one notation. If all A is point, we notation like this. Okay. We have example. Let XA is S1 and point, where S1 is circle. Then S1 K polyhedral product is union like this. This is a subset of M torus. When K is M disjoint points, the polyhedral product S1K is the wedge of M circles. When K consists of all proper subsets of M, the boundary of an M-1 dimensional simplex, S1K is fat wedge of M circles. It is obtained by removing the top dimensional cell from the M torus. Okay. For general K on M vertices, we have this subset. S1K, fat for wedge of M circles and M torus. Okay. Let XA is a real number and integer numbers. Then we have LK is RZK polyhedral product. When K consists of M disjoint points, LK is a grid in M-dimensional real space, consisting of all lines parallel to one of the coordinate axes and passing such integer points. When K is boundary of M-1 dimensional simplex, the complex LK is the union of all integer hyperplanes parallel to coordinate hyperplanes. Okay. We want in group theory tell about analog of K polyhedral product. Let J is a sequence of M discrete non-trivial groups. Let K is a simplicial complex on M, where M like this. Then we have the graph product of the group G1, Gm is like this, when where big star denotes the phi product of the groups. And we have relation Gi Gg equals Gg Gi for edges in simplicial complex. In fact, the graph product Gk depends only on the one skeleton of K. Okay. Let all Gi equals integer numbers. Then Gk is the right-angled Artin group, like this, where F is a phi group with M generators. When K is a full simplex, we have that right-angled Artin group isomorphic Zm, Z power M. When K is M points, we obtain a phi group of rank M. Second example, let Gi is Z2. Then Gk is the right-angled Coxeter group. Different from right-angled Artin group that we have relations that Gi square equals 1. Okay. We have theorem. Let RAK be a right-angled Artin group. Then fundamental group of S1K equals isomorphic right-angled Artin group. Both S1K and LK are aspherical if and only if K is flat. All higher homotopical groups isomorphic. And fundamental group of LK is isomorphic to the commutator subgroup of right-angled Artin group. Second theorem about right-angled Coxeter group. Fundamental group of Rp infinity K isomorphic RCK. Both spaces where Rk is a yield moment angle complex, this polyhedral product D1 is 0, K, are aspherical if and only if K is flat. All higher homotopical groups isomorphic, and fundamental group of Rk is isomorphic to the commutator subgroup right-angled Coxeter group. Okay. We have example. Let K be an M cycle, the boundary of an M GOM. A simple argument with Euler characteristic shows that Rk, D1 is 0, is homeomorphic to a closed orientable surface of genus like this. This observation goes back to a 1938 work of Coxeter. Therefore, the commutator subgroup of the corresponding right-angled Coxeter group RCK is a surface group. Similarly, when geometric realization of simplicial complex K isomorphic two-dimensional sphere, Rk is a three-dimensional manifold. Therefore, the commutator subgroup of the corresponding RCK is a three-manifold group. Okay. Theorem Panov and Veryovkin. Let right-angled Artin and right-angled Coxeter group RAK and RCK. Then the commutator subgroup right-angled arching group is phi if and only if one skeleton of K is a Hurdle graph. And the commutator subgroup of right-angled Coxeter group is phi if and only if one skeleton of K is a Hurdle graph. Part A is the result of Servatius, Droms, and Servatius. And the difference between A and B is that commutator subgroup right-angled arching group is infinitely generated, while the commutator subgroup right-angled Coxeter group is finitely generated. Okay. Let G be G group the commutator of two elements AB given by the formula like this commutator. We refer to the following nested commutator of length K as the simple nested commutator. Similarly, we define simple nested Lie commutators like this. Okay. For any group G and any three elements ABC from G, the following whole width identities hold, where A power B is like this. Let H and W subgroups of G, then we define bracket H and W as the subgroup G generated by all commutators like this. In particular, the commutator subgroup G stroke of the group G is bracket G with G. For any group G, set gamma 1 from G equals G, and define inductively gamma k plus 1 from G is bracket gamma k from G with G. The resulting sequence of groups gamma 1, gamma 2, gamma k, and infinitely sequence is called the lower central series of G. Okay. If H is normal subgroup of G, we will use this notation. In particular, gamma k plus 1 normal subgroup in gamma k, and the quotient group gamma k by gamma k plus 1 is abelian. Denote LK like gamma k factor gamma k plus 1. And consider the direct sum like this, LG. Given an element AK from gamma k, we denote by AK with line its conjugacy class in the quotient group LK. If AK in gamma k and AL in gamma L, then commutator of AK and AL in gamma k plus L. Then the whole width identities imply that LG is a graded Lie algebra over Z with Lie bracket like this. The Lie algebra LJ is called the Lie algebra associated with the lower central series, or the associated Lie algebra of group G. Okay. There is an isomorphism for any k more or equal 0, where this is the reduced simple homology of group of Kg. Okay. Theorem Panov and Veryovkin. Let right-angled Coxeter group RCK Then the commutator subgroup RCK stroke has a finite minimal set of generators consisting of like this nested commutators like this, where I less j and more k1, more k2, and other more kl minus 2. And I not equals k all ks. And I is the smallest vertex in a connected component not containing G of the subcomplex. This. We have corollary. The free abelian group H1 from Rk of rank like this has a basis consisting of the images of the iterated commutators described in this theorem. Okay. Let G be a group with generators Gi. The K theorem gamma K of the lower central series is generated by simple nested commutators of length greater than or equal to K in generators and their inverses. Corollary, let RCK be a right-angled Coxeter group with generators Gi, then the group gamma K is generated by commutators of length greater than or equal to K in generators Gi, because Gi is inverse for himself. The square of any element of gamma K is contained in gamma K plus 1 for right-angled Coxeter group is important. Okay, proof that. We use gamma K instead of gamma K from RCK in this proof for easy notation. Let A from gamma K. If K equals 1, then A like this. If K more 1, then A like this, where AI is commutator like this or commutator like this for BI from gamma K minus 1. We use induction on N. For N equals 1, the case K equals 1 is obvious. If K more 1, then we have that A like this or A like this, and we have these formulas. Okay. Suppose now the statement is proved for N minus 1. Let A equals this product, and A squared equals this product. We have that this product equals this. Clearly, the first factor lies in gamma to K. The second factor lies in gamma K plus 1 as a conjugate to A1 square by induction. And the last factor also lies in gamma K plus 1 by induction. Okay. We have corollary that LRCK is a Lie algebra over Z2. We do not buy FLZ2 is a free-graded Lie algebra over Z2 with n generators mu I, where degrees mu I equals 1. For any simplicial complex K, we consider the graph Lie algebra over Z2 like this. Relations Lie commutator of mu I mu G equals 0 for edges from simplicial complex K. Clearly, LK depends only on the one skeleton. However, as in the case of right-angled Coxeter groups, it is more convenient for us to work with simplicial complex. There is epimorphism of Lie algebras LK and LRCK. LRCK is a Lie algebra over Z2 generated by the elements GI with line. Its conjugacy class in this factor. By definition of a Lie algebra, we have this epimorphism mu I to GI with line. Since there is a relation for edge in K in the Lie algebra LRCK, the epimorphism factor through a required epimorphism phi. But in fact, the homomorphism phi from the proposition this is not injective, and the Lie algebras LK and LRCK are not isomorphic. This distinguishes the case of right-angled Coxeter groups from the case of the right-angled affine groups, where the associated Lie algebra LRAK is isomorphic to the graph Lie algebra over Z. Okay, example. Let K consist of two disjoint points, K, 1 and 2. Then LK is phi product FLZ2 mu1 FLZ2 mu2. The lower central series of RCK is follows: gamma 1 Z2 phi product Z2, and for K mod 2 we have that gamma K equals Z is an infinite cyclic group generated by the commutator like this of length K. Proposition 2 implies that gamma K by gamma K plus 1 equals Z2 for K mod 1, and gamma 1 factor gamma 2 Z2 plus Z2. Consider the algebra LRCK. From the arguments above, LRCK like this. It is easy to see that LK is a morphic graph algebra K graduate component for K 1 and 2. However, for K equals C, we have like this. But LCE from RCK equals Z2. Therefore, LCE from RCK is a morphic LCK factored by this relation. It follows that the homomorphism phi is not injective. Let K consist of two disjoint points. Then LRCK is a morphic graph algebra Lie factored by these relations, where A equals mu1 mu2. These infinitely relations. Okay. Let K be a simplicial complex on set M. Let RCK be the right-angled Coxeter group corresponding to K, and LRCK its associated Lie algebra. Then L1 RCK has a basis like this. L2 RCK has a basis consisting of the commutator like this with I less J and IJ not H. LCE RCK has a basis consisting of the commutators EGG with I less J for not H, EGK, E less J more K, where I not equals K. And I is a small vertex in a connected component like this, not containing G. We have corollary. Let K be a set of M disjoint points. Now, then we have that RCK is M product, phi product Z2. Then L1 has a basis like this. L2 has a basis consisting of these commutators, and LCE has a basis consisting of these commutators with this. Okay. Now we have example. Consider simplicial complex on psi vertices. Let K only psi disjoint points, then L psi RCK has a basis consisting of 5 commutators, like this. For K with one edge on psi vertices, L psi RCK has a basis consisting of psi commutators. And for K with 2 edges, L psi RCK is generated by the one commutator. Okay, I have else 4 minutes and quickly about proving this theory. For simplify notation, LK without RCK, gamma K without RCK for easy notation. L1 with this basis. Okay, we prove statement B. This about commutators length 2. We have abelianization map like this, and this group H1 is free abelian. Consider L2 is gamma 2 by gamma 3. The group L2 is Z2 module, and like this, for some M from natural numbers, we have a sequence of nested normal subgroups like this. Consider the exact sequence of abelian groups like this. Okay. Recall from corollary that the free abelian group, this factor is free abelian group Zn, has a basis consisting of the images of the iterated commutators with all different indices described in theorem above. The images of the commutators of length more or equals 3 are contained in the subgroup gamma 3 by gamma 2 stroke, like this. The group, this also contains commutators of length 3 with duplicate indices of the form like this. Therefore, the homomorphism psi, this homomorphism, acts by this formula, where indices different elements and these elements with the condition on the indices from theorem above. It follows that the two module L2 has a basis consisting of the elements like this with I less j. E and proving B and okay. We prove statement C. Consider LCI gamma 3 by gamma 4. The group LCI is a Z2 module, and we have the exact sequence of abelian groups like this. For the free abelian group gamma 3 by gamma 2 stroke, we will use the basis constructed in the proof of statement B. Elements of this basis corresponding to commutators of length more or equals 4 are contained in this. The group gamma 4 by gamma 2 stroke also contains commutators of length 4 with repeated indices. These commutators have one of the following 9 types: A, B. For all commutators with these types, we do formulas and okay. Like this, my time is ended. Okay, like this, similarly, statement B, and get this homomorphism acts by these formulas, and this and proof of statement C. Okay, this paper with these results, and thank you for your attention.